Hey everybody, Dr. A here, and in this video we're going to be exploring another example of sketching a qualitative influence line using the Muller-Breslau principle. So let's dive into it. In the given information, we're being asked to sketch the shape of the influence line using the Muller-Breslau principle for the shear force at point B, VB. So if you notice, we have a compound beam here, okay? We have a roller at A, another roller at C, an internal hinge at D, and an external pin at E. Okay, so this is still statically determinate, no problem. It's just a compound beam due to the fact that we have this internal hinge here. Now, again, we want to use the Muller-Breslau principle to sketch the shape of the influence line for the shear force at point B. Okay, now remember, if you're a little rusty on what influence lines are, go back and watch some of my previous videos. An influence line shows the variation of a particular load effect, in this case the shear force at B, as a dimensionless unit load moves across the beam. Okay, so we're always, in this problem, always going to be interested in VB, but the plot or the lines that we're going to draw show how VB changes as a moving load would move across this beam. Okay, so let's go ahead and do that. The Muller-Breslau principle allows us to sketch the shape of an influence line without doing all the nitty-gritty calculations along the way. So we're going to say solution, and then what we're going to say is remove point B's ability to support VB by placing a roller guide there. And then we're going to place VB on the beam like an applied load and sketch the rigid body deformed shape. Okay, so that's ultimately what we're doing. So I'm going to turn the page and I'm going to go ahead and redraw that beam. Okay, and you know, we have we had a roller at A, we had a roller at C, we have an internal hinge at D, and a pin at E. Okay, and so what we're going to do is we're going to make a cut here at this point B, and so I'm going to take my eraser here. I'm going to kind of delete a little segment there, and I'm going to place a roller guide at point B. And remember, a roller guide will prevent point B from supporting a shear force, but it still can translate you know, maybe a moment in between here or a normal force. Okay, so remember, we're only removing the ability for point B to support an internal force, an internal shear force. Okay, and so then we're gonna put, you know, VB here and VB here. We place VB at the spot there as if it were an applied load, and we see how this thing is going to deform. Well, if I look at the left side, you're going to develop this kind of pivot and rotation here. Okay, other way. This pivot and rotation here. Okay, so that makes sense, right? You have this VB pulling down on the left side here, so this segment is going to rotate into this new red shape. Now, what's going to happen with the entire right side of this? Well, you're going to have VB that rolls this up, and then you're going to have a pivot point here. you're going to develop some kind of kink at D because of that internal hinge and another pivot point at E, okay? So what this is going to look like is something like this. Going to have this kink there. Let me draw that a little bit nicer for us. Pivot point and then a kink there, and then a pivot point here, okay? And then, of course, we have this discontinuity right here, okay? And so this in red is the shape of our influence line. One more time, we have this VB pulling down on the left side, causing the left segment to rotate like this. And then on the right side, VB is pointing up, so it causes that point to move up. You have this pivot point at the roller, and it extends down to a kink at the hinge at D, and then it kinks back up to the pivot point at D. At E. So this is the sketch of your influence line for the shear force at B here, okay? So that concludes this example. If you found this helpful, please hit like and subscribe and be on the lookout for other content like this. Thanks for watching.